Okay, so a little intro to polynomial functions. The linear functions and quadratic functions we've seen so far are part of a much larger group, the polynomial functions, and then here you see a fancy definition of what a polynomial function is. Okay, so that might be a little bit hard to read, so let's just look at some things that really are polynomial functions. So like I said, a linear function is a polynomial function because we just have a 2 multiplying a variable, and you can always add or subtract. An x squared is a polynomial function. It's okay to subtract, like I just said. In essence, it's okay to have any exponent up here as long as it's positive, and as long as we don't have anything else that's weird that's going on. So fractions are okay because they just represent numbers, because I could rewrite this one as 5x7 minus 3 over 2 times x squared, and then plus x, and then just minus 3 over 5. So polynomial functions. Here's some examples of things that are not polynomials. A square root function is not a polynomial function. One way that you could see that is if you could write this as x to the power of a half plus 3. Just keeping in mind that you have an index of 2 and an exponent of 1. So you can see that the exponent is a fraction, so that's not allowed. So we cannot have, and you can just say square roots if you have to explain that, or you could say fractional exponent. Okay, here the variable is in the bottom of the fraction, so you cannot divide by a variable either. So this is not a polynomial function. Actually, we know this as a hyperbolic. So it's not a polynomial because you cannot divide. Sorry, it's a little early. We cannot divide by the variable either. And then finally here we have an exponential function, and so the variable is not allowed to be the exponent either. So it's okay to have an exponent on the variable, but not for the variable to be the exponent. So the variable cannot be the exponent. Usually what I do is when I assign these to you, I'll ask you to tell me if it's a polynomial or not. If it is, you usually don't have to tell me why, because that might be a little hard to explain. But if it's not, you should be able to give me a good reason. So that's what you'll see on your homework. So polynomials have specific types of graph in terms of what they look like. So let's look at one that we sort of know. So keep in mind that this is a quadratic. So the vertex here, hopefully you can see that the vertex here, this might be a while back, but the vertex would be at 3, because you take the opposite of that one and 1. So if I go to 1, 2, 3, and 1, I can put a dot there. And then this 2 here tells me that I go up twice as fast as I used to. So it's a long time ago, but x squared, if you plug in an x and you look at your y's, when you plug in 0, you're at 0. At 1, you would be at 1. At 2, you'd be at 4. And at 3, you would be at 9. So you should be going up by 1, up by 3, up by 5. So these are the numbers that change. So I don't go up by 1. My next dot will be going up by 2. And then obviously we have symmetry. And then the next dot, we're not going up by 3, we'll be going up by 6. So 1, 2, 3, 4, 5, 6. Cheating a little bit so that it fits. And then the same thing on this side. And then I clearly cannot get anything else on there. So here is a polynomial function. Okay, and if I had to describe the polynomial function, there would be 2 words that I'm looking for. A polynomial function is always smooth and continuous. Okay, the smooth is a little easier to probably understand. So nice and smooth, no sharp edges, no corners. Okay, so this is not allowed, this is not allowed. Okay, so no corners. And the continuous means that there really isn't, there aren't any holes or gaps in the graph. So here do you see it is smooth and continuous here, but then here's a gap, and then it comes back to being smooth and continuous on this little stretch. So but because of this, we'd say that this one is not continuous. So it's usually pretty easy to see if a function is a polynomial if you have a graph. Okay. Polynomials are named, usually. One of the ways we do it is give polynomials a specific name. So here are some examples of specific names. So f of x is 0, it's called the 0 function. That would be a 0, or it doesn't have any degree. If the if this number is anything but 0, it's called a 0 degree, and it comes from this. It comes from f of x is equal to 5. It's a constant function, a horizontal line at 5, and you could put an x to the power of 0 over here. Okay, and that's where that 0 degree comes from, because anything to the power of 0 is 1. So this one actually would be 5 times 1, and you are be back at 5. Linears, we've seen enough of those. So 2x minus 7. Quadratics, we just saw one of those. Okay, and then here are the characteristics of some of those things. So obviously we can have an exponent larger than 2. So what do we call it then? Well, if it's a 3, we still have a name for it. You could call it a cube. Okay, or you could just say it's a third degree. Okay, so we're looking for our largest exponents. So this is a third degree, and then I want to introduce this at this point, I guess, leading coefficient here. So the leading coefficient refers to what number is with the third degree. So the leading coefficient here is a -4, and that's important because it tells us some stuff about the graph. So here the largest exponent is 4, so this you can just call this a fourth degree. They do have a name for it, but you don't really have to know that. That's degree. And the leading coefficient here is 3 over 5. Because again, keep in mind you could write this as 3 over 5 x4. The leading the degree here is the largest one is that 7. So if it's not in order, this is still considered the degree of the function. So this is a 7th degree, and the leading coefficient for this one is a -5. Okay. Like I said, that information gives us the degree, and the leading coefficient gives us some information about what the graph would look like. So for example, almost all x squareds that we know, so let's do it x squared minus 5. So an x squared minus 5, from transformations, hopefully you'll remember that the picture would have looked a whole lot like this, with this being at a -5. Okay, so now let's look at it from a degree standpoint. So this is, the degree here is 2, and it's a 1 in front, so the leading coefficient, so I'm going to abbreviate that, the leading coefficient is a 1. So what does the 2 mean? Well, it means that you could have 2 solutions. You don't have to, but you could. And the leading coefficient of 1, as long as this is positive, so 1 is positive, this will go up. See how the graph goes up here and here? Okay, I want to emphasize the x squared part and the degree being that, meaning that there could be 2, because we've seen this, and I have to pick it a little bit careful. What if I pick x squared plus 5? This one's still going to go up because of that, right? And the degree is still 1. So the degree here, the degree is still 2, and the leading coefficient here is still 1. But this graph would run through the x, or the y-axis right there, and then go up. So how many solutions do you have? Okay, we don't have any solutions because it doesn't cross the x-axis. So the degree tells you what you could have. Okay, so here's another one. Let's do a -2x cubed plus 5x squared minus 7. Okay, so what would the overall shape of this be? Well, if the degree is 3, that means that there could be 3 answers, and then the -2 means that it goes down. So just mark three solutions, and if it goes down, then on this side the graph has to do this, right? So alright, so let's see what happens there. So if you just sort of backtrack, so it has to cross there, it's smooth and continuous, so it's got to curl back at some point. It's smooth and continuous, so it's got to curl back sometimes. So this is a reasonable guess at what the shape might look like. Now we may not get 3 solutions. Okay, is it possible to have less than 3? Certainly is. If you look at this, and I'll do another color, if I make this thing wiggle up here, so if I just shifted this graph up a little bit, so this one went here, this one went there. Do you see that now I only have 1 solution? So this is a third degree, and you can just count the humps. If you have 2 humps, it's a third degree, and then this one only has 1 solution. Okay, but that's sort of the overall picture there. So we'll do one more. So I want to go back to red. So let's do just x to the 4th, and 5x cubed minus 10. So degree is 4, so it could have 4 answers, and the 1 here, well, let's make it a number other than 1. We'll make it a 3. So the 3 means that it goes up. So fourth degree could have 1, 2, 3, 4 answers. The function has to go up, so going up means that on the right side it has to do this. Just like the quadratic, when it went up, on the right side it went up. And then you just wiggle your way back to the end. So cross, 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 cross. So that's what a fourth degree could look like. Okay? That's it. Thank you. Have a great day.